and we'll go through sort of some of the interesting, thought processes that are involved in designing an automaton to solve a problem. Now that's kind of like writing a program. Okay? I give you a problem, you write a program to solve it. Okay? And so, very often some kind of creativity is involved, so there are no real rules for this. You just have to think about the problem and design the automaton. So let's do some examples. Okay? So here's a language. It's just 0, 1. This is the string 0, 1. Incidentally, okay, what if I wanted to also accept the empty string here? Okay, so think about that problem. What if I wanted to accept the empty string here? What would I do? Okay. So I wanted n greater equal to 0. How would I change my automaton? Okay, so let's consider this language. It's a very simple language. It's an example of a finite language. Okay, and I have to design an automaton that accepts this finite language. It's just containing the string 0, 1. So everything else you must say no. Turns out that even though the language is very simple, this is not a trivial problem. We have to think about it and solve it in a systematic way. And you can pretty much use this systematic way for any finite language. So in some sense, I'm demonstrating to you that any finite language can be solved by a DFA, by a finite automaton. Okay. So as usual, we're going to start in our start state Q0. Okay. Now, if I get no string, I'm not going to accept. So this cannot be an accept state. If I wanted to accept the empty string, my start state would have to be an accept state. Okay. Now here's my thought process for how I'm going to build the machine that accepts this language. And now I highly encourage you, go for it. I'll give you a few seconds. Go try to build a machine that solves that language. Okay, I'll give you 5 seconds. 1, 2, 3, 4, 5. Okay. Now, if you're coming back, if you paused and solved it, great. If you're coming back just for the ride, here's my thought process for solving this problem. Okay. So, first thing I look at is the string 0, 1. It doesn't start with a 1. So if I'm going to see a bit 1, if I see a 1, I'm done. I can immediately reject. So let me move into a state. Now, of course, I said we typically label the states Q0, Q1, Q2, and so on, but you can choose whatever labels you want, and it helps a lot to choose labels that remind you of what's going on. So I'm going to call this the error state E. Okay. If I start with a 1, I go into the error state, and I'm never going to leave this error state. Okay. So when we're done with all the bits, I'm going to reject. I'm going to say no. Okay. So think of that as an error state. Now, the reason I don't immediately, jump up and down and say no is because those are not the rules by which these finite automata operate. Okay. Even though technically by human intuition, human logic, we know that once you get here, because it's a sink, you're going to reject, you could stop the computation. That's not the way finite automata work. So that's not the way programs work. When you're running the program, it runs until execution end. Okay. So it's going to continue processing all the bits. Even if you get 0, 1, 0, 1, 0, 0, 0, 0, and so on, it'll still process and stay here. Okay, on the other hand, if I get a 0, okay, I'm going to transition to a state Q1. Now, supposing I don't get any more bits, I cannot accept. So this is not an accepting state. Okay? So I cannot call this an accepting state because then I would accept just the bit 0. Okay? So you can think of this as the state. I've partially seen the string and I'm waiting. What am I waiting for? I'm waiting for 1. Okay? So if I find a 1, if the 1 comes next, okay, then I should be ready to accept. So let me call this state Q2, and this is an accept state, and now I'm not going to use green, I'm going to use the 2 circles. Imagine that I've colored it beautifully with green. Okay, so if I get a 0 or a 1, I'm ready to accept. Okay, now this is not a well-defined automaton yet, because you have to tell me what to do if in this state I didn't get a 1. If I got a 0, it means I've seen the string 0, 0, but that's not here. It's not in my set, so I had better go into this, error state. So if I see 0, 0, I'm done. Okay. What about here? You have to tell me what to do if more bits come. So you've got 0, 1, but if 0, 1, 0 comes, then I know it's not the string and I should reject. If I get 0, 1, 1, I know it's not the string and I should reject. So if any other string comes, if any other bit comes, I should reject. So there. And that's the complete automaton. Okay. So now you can compare this with your solution and see if you got this solution. If you did, fantastic. Okay. Meanwhile, If you didn't, sit down and see if you understood, go through the logic of how we created this and give yourself another problem. Maybe try, can I construct an automaton that recognizes the language 0, 1, and 1, 1? Okay, so exercise. What about the language 0, 1, 1, 1? Okay. Well, you see, it's similar, except that in this one, you cannot immediately go to the error state because you never know. Maybe another one will come. So you're not quite ready to declare no. Okay. But see if you can design this automaton. Basically, any finite language can be done with an automaton if you sit down and put the effort and do it. Okay. Let's take another couple of examples. Okay. The vending machine. So this takes us closer to reality. So you've seen a vending machine. I claim it's just a finite automaton. So let me describe for you, the vending machine. So in the vending machine, what do we have? We have, you can accept coins. And let's assume that the vending machine takes 5-cent and 10-cent coins. So this is just a real world example of an automaton. So, and let's imagine that a Coke costs 25 cents. So every time the machine gets 25 cents, it should spit out a Coke. Okay. So, initially the machine starts in some state. Okay. And we typically call that Q0, but now I'm going to use labels to tell me what's going on. I'm going to call that the 0-cent state. Okay. So this is where we start. Okay, now I'm going to imagine you're putting coins in. Think of the coins as the input sequence. So we've deviated a little bit from binary strings because we're interested in, real world applications now. Since this machine only takes 5 and 10 cent coins, you can think of the 5 as 0 and the 10 as 1. And the string of 5 and 10 cent coins that have been put in can be represented by a string of zeros and ones if you want. But let's just keep with the real world and talk about 5 and 10 cent inputs. The sequence of 5 and 10 cent coins that come in, tells the machine what to do. Okay. If it gets a 5-cent coin, well, it should transition. So 5-cent coin, it should transition. Well, what's the natural state into which it should transition? Well, I was in 0 cents. Now I've got 5 cents. So I have 5 cents in me. So think of the state of this machine that I'm building as storing how much money I have. How natural is that? Okay. And so tell me, if I'm in my 0-cent state and someone put in a 10-cent coin, what state should I go to? That's not hard. If you give me a 10-cent coin, I'm going to go to the 10-cent state. Okay? There are no other coins. So from 0 cents, I can either go to the 5-cent or the 10-cent state. Now it gets interesting. From the 5-cent state, maybe someone has already put in 5 cents, so I'm in the 5-cent state. Now you can put in a 5-cent or a 10-cent coin. If you put in a 5-cent coin, I go to the 10-cent state. If you put in a 10-cent coin, this is where it gets interesting. I go to the 15-cent state. Okay. What about here? If you have 10 cents and you get a 5-cent coin, you go to the 15-cent state. If you have 10 cents and you get a 10-cent coin, you go to the 20-cent state. If you have 15 cents and you get a 5-cent coin, you go to the 20-cent state. If you have 15 cents and you get a 10-cent coin, now this gets very interesting. Okay. Well, in theory, you have 25 cents, but you have to send out a Coke. When you send out the Coke, you got to charge that 25 cents. So actually, you go to the 0-cent state with a 10-cent coin. Okay. But I will label this with an action also. So not only do you transition, but you dispense a Coke. Okay, because you have 25 cents. And so you dispense the Coke, your 25 cents goes to 0, so you go to the 0-cent state. What about from 20 cents? Well, if you get a 5-cent input, similar process. You have 25 cents, dispense the Coke, and come down to 0 cents. Okay, so far, this is 10 cents, or this is 5 cents. This is 10 cents. This is 5 cents. Okay, but this is 10 cents. So I'm just labeling all the. If you get a 5-cent input from 20 cents, you go to 0 and output a Coke. What happens if you get 10 cents in the 20-cent state? That's interesting also. Okay. Now you have 30 cents. Well, technically, you don't have 25 cents, but you have more than 25 cents. So you should certainly output a Coke. Okay, but where do you go to? Well, after you output the Coke, you have 30 cents minus 25. Okay, so you should go to the 5-cent state. 30 minus 25 is 5. So if you get an input of 10 cents, okay, you output a Coke and transition to the 5-cent state. And there it is. That's the operating of the vending machine. The vending machine is a finite state machine, except that you've augmented some of the transitions, okay, the edges that take you from one state to another. You've augmented some of the transitions with some other action as well. So you not only transition states, but you reach, take a Coke, and dump it. Okay? Finite state machine. So the vending machine is a very simple finite state machine. But, finite state machines can do all kinds of complicated things. Okay? So let's take another example. Couple more examples of designing finite state machines. So that's the vending machine. Okay, so let me specify two languages. L1 equals strings with a 0. So they could have more than one 0, but they have at least one 0. And L2 is strings ending in 1. Okay, so let me show you that I can represent both of these with regular expressions. So this is strings with a 0 is sigma star. Remember what sigma is. Sigma is the alphabet 0, 1, and then the star takes all concatenation. So this is all possible binary strings followed by a 0 followed by sigma star. Okay, so that's as a regular expression. And now sometimes we don't want to keep writing sigma star. Okay, and so we have this wildcard symbol which we just call star, 0 star. And this was exactly the kind of format that I showed you in the first example of a regular expression, ls, list, fox, star. Fox concatenated with sigma star. And this is the language, any string, but it must end in a 1. So it's sigma star, anything, followed by a 1. Okay. And anything could even be the empty string, okay, which, is the wildcard. We just typically call this the wildcard, followed by 1. Sometimes we even forget. Sometimes once we're experts, we don't even put the concatenate sign. We might just write this as star, 0, star. And the concatenation is implicit. We might write this as star, 1. Okay. Anything 0, anything. Anything 1. Okay, so let's build automata for these two problems. Okay, so now I'm going to pause the video. Or you pause the video. 1, 2, 3, 4, 5. Solve the problem. 1, 2, 3, 4, 5. Okay, here we go. Let me show you my logic, my intuition for how to build this automata. So, well, we usually start in my state Q0. Okay, and the empty string is not accepted because, it must have at least a 0, so I cannot accept the empty string. Now, okay, if I get a 0, okay, so if I get a 0, actually I'm ready to accept because all I need is 1 0 in my string. So I'm ready to accept. So I'm ready to accept in my state Q1. So I'm going to call it an accept state. And in fact, it doesn't matter if any other strings come. If any other bits come, I'm ready to accept. So this becomes a black hole state. But unlike the previous example where the black hole state was an error state, a no state, in this case, the black hole state is a yes state. So you cannot leave this state no matter what comes, no matter what 0s and 1s comes, because you've already found the 0 that you need to accept. Okay. On the other hand, now you're in state Q0, if 1s come, you just don't leave this state. You stay in this state. Okay. You think of this state, the 0 state, as I'm waiting for a 0. So 1, 1, 1, 1, 1, I stay in this state. 0 comes, boom, ready to accept. It's a black hole state. Okay. Now, I've shown a particularly efficient way of, building a machine to solve that problem. You might have solved it with 3 states or 4 states. That's not a big deal. Don't worry. As long as your solution is correct. Now, yes, just like programmers like to find the smallest program that can solve a problem, people are interested in the smallest finite state machine that can solve a problem and so on and so forth. But for the moment, we're happy with just some finite state machine that solves the problem. Okay. So if you did it with 3 states, don't worry about it. It's a good solution. Okay, let's talk about strings that end in a 1. That's a bit harder. This one's easy because, the moment you see a 0, you're ready to accept. Strings that end in a 1. Okay, so let's perform the usual logic. We start in my start state Q0. Okay. As long as I see 0s, I'm not going to leave the start state. It's kind of like here where I see 1s. So if I see 0s, I stay here. I'm not going to budge. The moment you give me a 1, I feel like I'm ready to accept. You've given me a 1. I'm ready to accept. Okay, so I'm ready to accept. Let's call this Q1. I'm ready to accept. And if I make this a black hole state that's ready to accept, the problem that will arise is that if another 0 comes and that's it, my string doesn't end in 1. So I cannot make this a black hole state. I can make this I can stay in this state as long as I continue to get 1s. Okay, as long as I continue to get 1s. Okay. But if I get a 0, I have to go back to this waiting for a 1 state. So you can think of this as waiting for a 1. I get my 1, ready to accept as long as I keep getting 1s. If I get a 0, I go back to the waiting for a 1 state because I have to end in a 1. So the only case where I can stay in this state is if the last bit is 1. Okay. Now if you solve this problem, again, you might have used 3 states, 4 states. That's not a big deal. Okay. But try to sort of get good at looking at a problem and trying to visualize the process of constructing a finite state automaton to solve the problem. Okay, so here are 2 example languages. Now, let's see if I can do even more complicated languages. Okay. So let me erase here.